In this video, I'm going to focus on rotational kinematics. Let's start with what the motion is. Previously, we've discussed motion along the circumference of a circle. We defined that as circular motion, and that would be like the Earth going around the sun, and why we have years. Now we're talking about an object spinning on its own axis. That's called a rotational motion. This is like the Earth spinning around its own axis, and is why we have days. Let's look at an example to help us differentiate between linear and rotational variables. Here we have the overhead view of a spinning disk. The disk is going to rotate counterclockwise, and two positions are marked. We've got position A, which is closer to center, and B, which is closer to the edge. Two questions we're trying to answer. Think about looking at the disk in one full spin. We're wondering which position moved faster, and also which position rotated faster. To answer question number one, let's let the disk rotate a fraction of its overall spin. Our positions A and B started on this horizontal brown line, and we let them rotate to this brown line. So our positions moved for the same amount of time. Because position B is closer to the edge than is position A, it would travel a greater circumference around its circular path. And because it has a greater distance traveled over the same time interval, we would say that it's moving faster. Velocity is related to how fast the object moves, so we would say the velocity of B is greater than the velocity of A. To answer question number two, we'll look at the same time frame from brown line to brown line. So again, our positions are moving for the same amount of time. But now we're focused on their angular displacement, or how quickly they're changing their angle relative to their full circular path. If we let this brown line rotate all the way around and wind up back where it started, we would find that positions A and B would complete a circle at the same time. So we can conclude that positions A and B are changing their angle at the same rate. Angular velocity is about how fast an object rotates or changes its angle, and these are doing so at the same rate. So we would say their angular velocities are equal. When we study linear variables, we focus on our directions as up, down, left, and right. There are 6 important kinematic variables to know. Their variable labels are shown in the green column, and their units of measure in the yellow column. When we study rotational variables, we have new directions, now clockwise and counterclockwise. In place of position, we have angular position and the variable theta. In place of starting position, we have starting angular position, the variable theta naught. In place of velocity, we have angular velocity, the variable omega. Starting velocity is starting angular velocity, omega naught. Acceleration is angular acceleration, the variable alpha. And time is the same, still t. Notice our units have changed from meters into radians, radians per second, and radians per second squared. So we're studying a rotational spinning motion and not a linear straight line motion. Here we're looking at our 3 kinematic equations. These are for linear motion. And as we build our rotational kinematic equations, observe that we're just placing the new variable in place of the old. Equation number 1, we're just substituting v with omega, a for alpha, and v naught with omega naught. Equation 2 has similar substitutions and now also putting theta in place of x, and the same substitutions for equation 3. So we use these for rotational motion, just like we would use our old 3 equations for linear motion. Here, looking at conversions, if you want to convert your angle measurement from degrees into radians, you can use the conversion in the white box. Multiplying your angle measured in degrees by the quantity pi over 180 will turn it into an angle measurement in radians. If you want to convert from rotations into radians, multiply the number of rotations you have by 2 pi. Here we have a conversion from linear velocity to angular velocity, and here a conversion from linear acceleration to angular acceleration. Note that the variable r stands for radius, so multiplying the rotational variable by radius will turn it back into the linear variable. Back in our circular motion unit, we discussed our velocity equation as circumference divided by period. We built this equation through our conceptual understanding of circular motion and constant speed. But now that we've gone over our conversion between linear velocity and angular velocity, we can use that with our period and angular velocity conversion to build the equation through substitution. I just wanted to show you an additional way to build the equation at the bottom of your screen. Finally, let's talk about rotational directions. Counterclockwise is the known positive direction for rotational motion, and clockwise is the known negative direction for rotational motion. When you solve a problem, you can just state clockwise or counterclockwise at the end of it as a way to avoid these positive and negative signs.